Hey everybody, Mr. Mueller here. So in today's video, we want to talk about conservation of energy. So the key component of conservation of energy is that energy is neither created nor destroyed. It is only transformed from one form to another. So what this means, and a lot of times in physics we like to describe things mathematically, is that the energy at the beginning of a situation is always equal to the energy at the end. Okay, and in particular, we can say the sum of the energies at the beginning. That was a terrible sigma. There we go. Is equal to the sum of the energies at the end. All right. So in every situation, we'd say energy is conserved. It's never created nor destroyed. So let's look at it. Let's review a couple of our different formulas for energy and then get into some example problems that we'll see from the lessons. So one of our first ones is kinetic energy. This is our energy of motion. That's going to be 1/2 mv squared. Our next big equation is potential energy due to gravity. And that's going to be mass times gravity times the height. Okay, mass, gravity, height. And then our next one we're going to have is the potential energy due to a spring. We'll call it PES. And that's going to be so 1/2 kx squared. 1/2 kx squared. Those are our equations for energy. And the potential energies and the kinetic energies all going to add up in a particular way. So let's take those equations and then let's apply them to some situations. So in our first situation here, we've got a roller coaster. Okay, we got a roller coaster. And so this roller coaster is traveling 55 meters per second at the bottom of the first hill. So if we imagine we have our roller coaster there, we got a little cart right up here. It started up here, it goes down the hill, and at the bottom of the hill, we know it's got a speed of 55 meters per second. So we know how fast it's going. We don't know what happened in between. And the nice thing about energy is it allows us to figure out what happens at the beginning, what happens at the end, and we don't really care about what happens in the middle. Because maybe it's really complicated or hairy. Energy allows us to kind of go between those two very easily. So let's talk about how we would do that. So if we think about at the beginning, so the initial spot, I, okay? Generally, when you're thinking about a roller coaster, it gets to the top of that hill and you're barely moving. You're going really, really slow. So we're just going to kind of assume that that cart sits almost still. And so here at the top of the hill, at the top, we're going to have all potential energy. It's all going to be potential energy due to gravity. So we can say that's mgh. So at the top of the hill, it's all mgh. At the end here, so at the end, we are going the fastest possible. So when you come down that hill on the roller coaster, you're going as fast as possible at the bottom. That's what gives all the exhilaration, is you're going really, really fast at the bottom. And so all of that potential energy has now transformed into kinetic energy. So this will be at our bottom of the hill, and this is going to be kinetic energy. So 1/2 mv squared. So because, again, back to our original equation, energy is neither created nor destroyed, it's going to be equal. So we can say the potential energy due to gravity is equal to the kinetic energy at the end. Those are going to be the same. So what we'd say is mgh is equal to 1/2 mv squared. And now we just do some algebra from that. So if we look here at the problem more closely, they do ask how tall must the hill be. So that means we're clearly looking for the height. How tall is this thing? So if we look, the masses cancel here, which is kind of handy. A lot of times when we set them equal to each other, they're going to cancel. And then we know what gravity is. Gravity is going to be 9.8 meters per second. 1/2 is a constant, and we know that the velocity is 55. So now we just have to solve for h, moving things around a little bit here. Let's see if I can move things up here a little bit. Let's see, let me scroll. No, it's not. All right, so moving things around a little bit over here. We end up with, let's see, I'm solving for h here. So we're going to get h here. Sorry, I had a brain fart there. H is equal to 1/2 multiplied by v squared over g. And so now we just have to plug in our values. And so we're going to get 1/2 multiplied by 55 squared all over 9.8 meters per second squared. And so that's going to give us a number there. Doing some quick math there, we end up with 154.3 meters would be our height there. So it's pretty tall roller coaster there. Okay, so there we have it. We can continue on doing more energy problems like that. And here we have another one. So we have an 800 Newton diver dives from a diving board of 12 meters above the water surface. If the diver leaves the board with an initial speed of 2 meters per second, what is the diver's speed when striking the water? So here's what we're going to kind of assume here. So we got our diving board. Again, I like to draw pictures here. Here's our little diver here. And so at the beginning, we have a couple things going on. Now, this is where things get a little dicey because we don't just have potential energy here. We also have some mechanical energy here going on as well. So the diver starts here at the beginning, and at the end, the diver is diving into the water, right? Get really skinny. Here's the water going in the water. Okay, and so we want to know what's the velocity here when they hit the water. So clearly there's going to be something going on with kinetic energy. So at the beginning here, now we have two pieces of energy. Not only do we have potential energy because there's some height here that we have to go. So there's 12 meters above the water surface. That's a really high diving board. We're also going to have some movement. So we know the diver jumps or whatever and gets some lift. So they have some movement there as well. So at the beginning here, we have potential energy, but we also have some kinetic energy. And so those two combine to make a total amount of energy. Now at the bottom of their dive, so they've dropped 12 meters. It's going to be completely kinetic energy. And so now we can set up our equation here. So we know that these two guys are going to have to be equal to each other because energy is conserved. So we can say the potential energy is going to be equal to mass times gravity times height. Mass times gravity times height. And the kinetic energy is going to be 1/2 mv squared. And then on the right-hand side, we know it's going to be completely 1/2 mv squared. And so it's important to note that these velocities are going to be different. So it's good to add a subscript there at the bottom to indicate, hey, where these are not the same velocity here. And so we do a little work. One nice thing about this here is we have a mass here and we have a mass here. So we do a little algebra. We can factor those guys out. So we have m out front. That's going to be GH plus 1/2 V squared. It's equal to 1/2 mv squared final. So that would be our initial up here. And what we see here is so we can go ahead and actually cancel the masses here because it's factored out. So now we have a simpler equation to work with. There we go. And so we have GH plus 1/2 V naught squared is equal to 1/2 VF squared. Okay. Now it's just a matter of plugging values in and going. We know the height of the board, that's going to be our 12 meters. We know the velocity here, and we're looking for this final velocity as we strike the water. So we can plug in those numbers and get a value on the left-hand side, multiply by 2 and square root it and get a number that we like. So we'll go ahead and continue on there. So the number is going to look like this, 9.8 times our 12 plus 1/2 times 2 squared is equal to 1/2 times VF squared. I wrote that wrong there. Yeah, squared. Okay, so we can keep punching in some numbers there. So this number here on the left side would be 19.6 to 1/2 V squared, VF squared. Okay, continuing on here, and again, working through things, we're going to double that number. So we're going to get 239.2, and again, all I did was I multiplied by 2 to get rid of the 1/2. It's going to go VF squared, so I square root both sides, square root, and so V final is equal to 15.47 meters per second. And we'd have to check our sig leaks there, of course, but that's good enough for this example. Okay. All right. So another question maybe relating to energy. Here, this is a conceptual one. So ignoring the effects of air resistance, because air resistance causes friction, very complicated to measure and calculate. A ball falls freely towards the ground. Its total potential, the total mechanical energy will blank. What will it do? So if we think about the ball, so it's going to be some height here. It's going to be up here at the start. So this is our start. And after some time, at the end, the ball is going to be down here, right? And it's going to be moving. So some swishes behind it. It's moving, okay? So what's happening? Well, if we think about that here, at the top here, it's all potential energy. Okay, so it's all potential energy. And at the bottom here is all kinetic energy. And the beautiful thing about these two things is those are going to be equal. Every single time, those will be equal. So the energy is conserved here. And because we've raised that ball up into the air, we've given it potential energy, we drop it, that potential energy converts into kinetic energy. So that would continue to accelerate, it would get a really, really high velocity. It would end up being conserved here. So that it would be the same as where it started. Okay, so in this last problem, a child is jumping off a wall onto a trampoline, and I can't get over that the height is 16.4 meters, a super tall wall. Okay, so before they spring back up into the air, the trampoline compresses 1.8 meters. So what that means is all the energy from the jump is converted into the trampoline. All right, so what we can say here is at the beginning of our jump here, it's all potential energy due to gravity. And after our jump here, it's gone from potential energy due to gravity to kinetic energy into the spring. So now it converts from kinetic energy back into spring potential energy. And so we're going to have potential energy due to a spring, not gravity, a spring there. And so our equation here would be mgh is equal to 1/2 kx squared. And so now we just have to solve for m. So we divide by gh. And we plug in chug, excuse me. There we go. So I'm going to have my 1/2 times my 288 multiplied by 1.8 squared divided by 9.8 multiplied by 16.4 meters. And we plug in chug. And so then we see the mass of the child is, so we get a mass of 2.9 kilograms. So that child is very light. Maybe this is a baby bird or something like that. Anyways, so there are some examples related to energy and how you can use those in some different scenarios. So hope this video helps. God bless. Have a great night.